Now you may wonder, why so much of focus on the trigonometry of it. The reason is that we are going to start looking at intuition. So when you start looking at the intuition must correlate with the theory that we are studying. So what we are doing is to actually develop the theory so that the intuition becomes very straightforward for us to apply. Now to sort of emphasize this, what I'm going to do is look at our topics. Okay, our topics, where is that? 5.5 deals with something called an all-pass system. Now, because of our understanding that it's important for us to see how first order systems behave, I'm going to pick up section 5.5 and introduce the notion of an all-pass system and introduce some of the important things that we can learn from all-pass systems. So here is a brief introduction to section 5.5. all-pass systems using the concepts that we have already studied. So again, basically it's a reinforcement of the systems that we have studied. So all-pass systems. What are all-pass systems? What are their characteristics? How do they relate to what we have studied already? And then some important elements are going to be brought in this discussion. So the first thing is I'm going to ask you to consider a first order transfer function which has got a very unique structure. 1 minus a z inverse. That's the denominator, first order system. So you know exactly there is one pole located at z equal to a. And the numerator is z inverse minus a star. Okay, so the important aspect. So this is the structure I want you to look at. So now I'm going to do it the following. I'm going to factor out z inverse in the numerator. What I will get is 1 minus a conjugate z divided by 1 minus a z inverse. Okay, very interesting. Okay, now remember, we are always interested in the magnitude response, that means on the unit circle. So evaluate the z transform on the unit circle, becomes HAP e of j omega. Wherever there is z, you substitute e of j omega. So this becomes e power minus j omega 1 minus a conjugate e of j omega divided by 1 minus a e of minus j omega. Okay, now look at this very interesting property. The magnitude of this transfer function on the unit circle, HAP e of j omega, will be magnitude e of minus j omega. E of minus j omega, when you take the magnitude, will always be equal to 1. So this is always equal to 1. And then you have magnitude 1 minus a conjugate e of j omega divided by magnitude of 1 minus a e of minus j omega. Okay, now notice that if I call this as the denominator function d e of j omega by n e of j omega, that's the numerator. Notice that n e of j omega is equal to d conjugate e of j omega. Okay, basically it is, so we can write this as some complex number, let us call it as some complex number c, and the numerator is c conjugate, and we're looking at their magnitudes, right? Basically this is what we are looking at. So when you quantity and its complex conjugate will have the same magnitude, so therefore this ratio is equal to 1. So we have now verified that this transfer function has got a very unique property, and that unique property is that HAP e of j omega magnitude is equal to 1 for all frequencies. Okay, attenuate or amplify. All of them have got the same gain. So this is why it is called an all pass filter. All frequencies are passed with the same gain, an all pass filter or as an all pass system. Okay. Now there is a very interesting structure that is that you see in the between the numerator and denominator of an all pass system. So look at the denominator. So this is the n equal to 0, n equal to 1. So basically the coefficients are 1 minus a, right? 1 minus a z inverse. Okay. So if you look at n equal to minus 1, look at the numerator. What the numerator is very interesting. You see minus a conjugate and 1. So basically you sort of see, so what you see in the in between the numerator and denominator is that there is, first of all, there is conjugation and there is time reversal. Okay, there is time reversal, basically plus 1 went to minus 1, and there's a conjugation. And so there is a note, we note that in between the numerator and denominator, we notice that there is a time reversal and conjugation. Time reversal plus conjugation. Okay. And this basically tells us that I can now write down not only a first order all pass function, I can write down an arbitrary all pass function. General form of all pass systems. Okay. So HAP of Z, look at the denominator, 1 plus B1 Z inverse plus B2 Z minus 2 plus Bn Z power minus n. Okay. Now look at the time reversal and conjugation. So what will be the numerator? The numerator will be Bn conjugate as the first term, because now it's time reversed. The second term will be Bn minus 1 conjugate Z inverse. The next term will be Bn minus 2 conjugate Z minus 2, and so on. The last but one term will be B1 Z power minus n minus 1 B1 conjugate, and the last term will be Z power minus n. Okay. Now to verify, just factor out Z power minus n. What you will get is the following. You will get 1 plus B1 conjugate Z, B2 conjugate Z squared, all the way to Bn conjugate Z power n. Denominator will be 1 plus B1 Z inverse plus B2 Z minus 2 Bn Z power minus n. This is the denominator. Evaluate it on the unit circle. Verify that what you see is that the numerator and denominator are conjugates of each other, and therefore the magnitude will be equal to 1. So I will give you a task. Verify that HAPE of j omega magnitude is equal to 1 for all values of. So make sure that this is the very important aspect that I would like you to capture. All right. So here is the further understanding of what of the concepts that we are going to be looking at in today's discussion. Okay. So I want to now look at the zeros and poles of the all pass function HAP of Z. Okay, very important. Now if I want the all pass function to be causal and stable, causal and stable. Okay, what can you tell me about the poles? The poles, all the poles must be within the unit circle. Must be within the unit circle. Okay, and typically in a transfer function, the poles and zeros are not necessarily connected. I mean, you can have a set of poles and zeros are at a different location. However, in an all-pass function, there is a very interesting relationship. Remember, we got a relationship 1 minus a z inverse minus a1 conjugate, a conjugate. Okay, so where is the pole? The pole is at z equal to a. Where is the 0? 0 is at z equal to 1 by a conjugate. Okay, so I want you to first sketch the sketch this. All right. Okay, I have a unit circle so that I don't have to draw it, and so here is a way by which we can look at the, supposing I have a pole which is located at A. The pole should be inside the unit circle, so I'm going to mark it here. Okay, where is A conjugate? It will be the same radius at the negative angle. 1 by A conjugate, where will that be? It will be along the same line at the reciprocal location. This is what is, okay. So first thing to note is that the pole and the 0 are along the same line, they are at reciprocal locations. Okay, first thing to note. Second thing to note is that the behavior of the LTI of the all-pass function, as I start at the origin and as I go around the unit circle, remember I want to get the magnitude response, I traverse. At every point on the unit circle, the effect of the 0 and the effect of the pole are identical. So therefore the ratio becomes equal to 1. That's how you get an all-pass system. So now you have a very, very important result which comes from the study of all-pass systems. The following is this. Okay, so that is one of the reasons why we are studying all-pass systems. So supposing you look at the same location, but now rather than a pole, I'm going to look at a 0. And look at a 0 at the reciprocal conjugate location. Okay, what can you tell me? The effect of this 0 is the same as the effect of the 0 outside the unit circle, reciprocal conjugate location. Okay, both of them will give you the same magnitude response. So what do I mean by that? 1 minus a z inverse. Okay, this is one transfer function. The second transfer function is this, z inverse minus a conjugate. Both of these, let's call this as H1 and H2, both of these will have the same magnitude response. Okay, how did we get that? From the basically the discussion on all pass functions, we have obtained this. So when I am now designing an LTI system, I can put the zeros inside or outside in my design, because I know that 0 inside the unit circle gives the same response as the reciprocal conjugate location, 0 in the reciprocal conjugate location, and therefore I now have a flexibility in my design. Now why would I want the 0 to be inside the unit circle? Remember H inverse. Supposing I want to design a system which is invertible, then I want to have an LTI system which has got all zeros inside the unit circle. If I have a 0 outside the unit circle that comes up as part of my design, I can move it to the corresponding location inside the unit circle and still get the same behavior. So you see how we are starting to get some insights into the design of an LTI system based on this particular aspect. So for an all-pass system, the poles and zeros are at reciprocal conjugate locations. Now, supposing they were on the real axis, no problem. This is the pole. The zero will be located along the real axis, and you can see that this will be where the zero will be located. So, conjugate or now the only thing remaining is what happens if you specify that your all-pass filter will have real coefficients. If you specify that your all-pass function has got real coefficients, then you cannot get just one complex conjugate pole, you will get the complex conjugate pair. So basically there will be another pole which is also located at the conjugate location, which means that there will be a zero also at the conjugate location. So basically that's the unique insight that we have. This is how all-pass functions behave. Okay, and by the way, this is not only the result that we can get from an all-pass. We get some very interesting further results from the all-pass. So let me give you an indication of one more result. Again, it involves a lot of trigonometry, but I think at the end of the day you will appreciate what this particular result is going to give us. So let us look at a all-pass function HAP E of j omega, a first order all-pass function which is given by e power minus j omega 1 minus a conjugate e of j omega divided by 1 minus a e power minus j omega. Okay, let us write a as r e power j theta. Remember, we already wrote it down in this form. Once more, just for practice, verify that HAP E of j omega is equal to 1 for all values of omega. Just again substitute, verify, you make sure that you are comfortable with that. So the next step that we are going to be looking at is the argument of HAP E of j omega. Okay, remember, we always go the same way, but now there are two terms. So you have a first term which is e power minus j omega and a second term. The first term contributes a minus omega in terms of the phase, e power minus j omega. The phase, if you take only the phase part, it will be minus omega. The second term will give you a phase term which is given by tan inverse minus r sine of omega minus theta divided by 1 minus r cosine omega minus theta. Okay, make sure that you are writing down the terms correctly, and then we get the expressions appropriately. Okay, now I want you to take one more step. This is straightforward. I'm sure you will be able to do that. Compute the group delay. Okay, now this is non-trivial. I want you to take the time to actually go through the steps and compute that. So the group delay. So group delay of an all-pass function tau of omega, which will be minus d by d omega of argument of HAP E of j omega. Okay, there are two terms. When you differentiate the first term, it will give you a plus 1, because minus d by d omega of omega will be plus 1. And then you will get the following expression. Okay, oh, by the way, I missed one very important one. So what I've written down here, the first term is the numerator term. Remember, we have to also subtract out the phase of the denominator term. So the denominator term will be minus tan inverse of r sine omega minus theta divided by 1 minus r cosine omega minus theta. There are two terms, right? Numerator and denominator. So the first one corresponds to the phase of the numerator. This is the numerator, and this is the denominator. And because it's the denominator, we subtract Okay, there is subtraction between the numerator and denominator terms. So now when you take the expression, this will be, you can show that this can be written as minus 2 times d by d omega of tan inverse of r sine omega minus theta divided by 1 minus r cosine omega minus theta. Okay. Basically, these two terms are, the numerator and denominator are negatives of each other, because they are basically complex conjugates, so their angles are negative, or one is the negative of the other, so you can combine them. So the important step is that when you do the differentiation, make sure that you are careful to do, because you are differentiating the tan inverse function, make sure you get the correct result. So finally, when you finish the differentiation, this is what you should get. The tau of omega for a first order all pass function will be obtained as 1 minus r squared divided by 1 plus r squared minus 2r cosine of omega minus theta. Okay. Now, of course, you will go through many steps of algebra, and sometimes you may make some mistakes, and you won't get this final answer. But please make sure that you are getting this final answer. Very, very important. Okay. Why are we so insistent on this? Because the core of what an all-pass function will contribute is obtained from this particular expression. So now look with me to say that if you have a causal stable all-pass, okay, so then what we know, that this condition requires that all poles are inside the unit circle. All poles are inside the unit circle, strictly inside. They cannot be on the unit circle, it has to be less than. So this means that the pole is located at r e power j theta. This is the location of the pole. Location of the pole. So therefore, the r must be strictly less than 1 for it to be a causal stable all pass. Okay. Now look at what we have. If r is less than 1, tau of omega, think of it as a numerator and a denominator. So if r is less than 1, numerator is always greater than 0. Correct? Less than 1, numerator will be always greater than 0. If r is less than 1, denominator, what is denominator? What is the smallest value that denominator can take? 1 minus r the whole square, right? So the denominator is also greater than 0. Okay, how do I say that the denominator, the smallest value of denominator? Okay, the question is, can it be negative? So cosine of omega minus theta, the most negative value that it can take is minus 1. So then what you get is denominator is equal to 1 plus r squared. So you can, or the most positive number that it can take is plus 1. So 1 plus r squared minus 2r. That is equal to 1 minus r the whole squared. R is less than 1, so therefore denominator is also greater than 0. So this is a very important result, which says that if you have a causal stable all pass function, even from take it in the form of a first order term, you can say that tau of omega is greater than 0 for all values of omega. Okay, that means the group delay is always positive. This has a very significant implication in the following, because what is tau of omega is minus d by d omega of the argument of HAP E of j omega. Okay, so this, if tau of omega is greater than 0 for all values of omega, then the what this says is that the slope of the all-pass function, the phase of the all-pass function must be always negative, right? Only then the slope is negative, negative of the slope will be positive. So this implies that the argument of HAP E of j omega is a monotone decreasing function. Monotone decreasing function. Okay, what do we mean by that? If you plot the response of an all-pass function, okay, let's say it starts somewhere. It has to be decreasing all the time, right? It can decrease less, decrease more, but it cannot stay flat, because if it stays flat, what will happen in that region? The slope will become zero, the slope will become constant, group delay will become 0. So basically what you see is a monotone decreasing function. That is the so now if you have many all pass, basically it's not a first order, a second order, a third order, fourth order, doesn't matter, all of these terms will satisfy the same thing. So here is a general statement, general result, okay, causal stable all pass of higher order all pass. All pass system, all poles inside the unit circle, all poles strictly inside the unit circle, inside unit circle. This also means that the phase is monotone decreasing. Monotone decreasing. This is a very, very important property of an all-pass function, which we will come back to study in the later part of this chapter. But what other things? What have we summarized so far? We said that we will look at first-order systems. So we looked at a special case of a first-order system where there is a relationship between the numerator and the denominator. We said that the 0 and the pole are at reciprocal conjugate locations. The coefficients, they are mirror image and time reverse and conjugated in terms of their the sequence in which they appear, and this will satisfy that HE of j omega, the magnitude response is always equal to 1. And we went ahead and calculated what is the magnitude response, the phase response, and the group delay. And the group delay we showed was always greater than 0 for all values of omega, which then requires the phase to be monotone decreasing, and that is a property that we will utilize in our understanding of our LTI systems. Okay, so here is a important aspect that we want to capture in terms of our all-pass functions. All-pass functions from a first order or a higher order term, we can say that if you want the condition of causal and stable, all poles must be strictly inside. Maybe make sure you capture that. It should be strictly inside the unit circle, and the phase that will give you a phase that is monotone decreasing.